you. Kanagawa is a hardware language at Microsoft. It's been sort of internal up to this point, developed for many years, but we plan to open source it. It's a big thing. I'm really going to focus on the threading model today, which I think is the key novel aspect that we described in the paper. So I'm going to talk a little bit about the design goals, spend most of my time on the threading model, show you just a taste of the results, and talk about open problems that would be interesting for collaboration. So it's a typical hardware thing. You have high-level source code coming in. You give that to the compiler. It gives you synthesizable system Verilog. And then you can feed that to a standard tool for FPGA or ASIC implementation. At Microsoft, IP generated by Kanagawa is broadly deployed on FPGAs in the data center. So we have two design goals for the language that are really relevant here. The first is that the code should be high-level and abstract. And there's two pieces to that. The first is that the language itself is missing unnecessary details, all the tedium is sort of removed. The second is the language enables the development of abstractions in libraries, which then makes code that uses those libraries itself more abstract. The second is the language should be easy to reason about. You should be able to look at the code and talk about the performance and the correctness and be pretty confident in your predictions. So I've been on this project a long time. One question that has eluded me, and I think might still elude me, is what exactly is a hardware description language? I found this description from a paper on Verilog, which says, HDL is a programming language with special facilities for dealing with the problems of hardware. One of those special problems in hardware is parallelism. And so it's an HDL is a language that really lets you use the parallelism that Moore's law gives you. And that sounded good, except for now you think about it for a minute, and that's really quaint, because it implies this world where the hardware people deal with parallelism and the software people deal with sequential code. And we all know that sort of fell down. And I was going to talk a bit more, but then insert the keynote from day one here. And David Patterson described it as the hardware industry throwing a Hail Mary pass in American football, hoping the software engineers would catch it and be able to sort of shoulder some of the burden of dealing with parallelism rather than hiding that all on the hardware side. So the idea with Kanagawa is let's complete this circle. If shared memory multithreading is a standard paradigm that seems to work well, it's a cliche maybe for this audience, but it works well for people writing imperative code to sort of take on some of this responsibility of utilizing parallelism. Why don't we just try that for hardware itself? And so we'll express shared memory concurrency in the language and map that directly to hardware. And that's the way we utilize the parallelism of hardware. So the secret sauce to make this work is our special threading model, which is a lot like standard multithreading, but there's a key difference, and that's what I'm going to describe now. That's where I'm going to spend most of my time. It both makes the mapping to hardware very straightforward, so the compiler can be simple, and therefore you get very predictable performance, and it's also much easier to reason about at the source level than traditional multithreading. So our threading model, we call it Wavefront threading. Here's some just standard Kanagawa code. It just looks like regular old imperative code. You could say this is C++ or something like it. So here's a thread, the blue thread that comes and starts executing code in this function at some point in time. And it moves down through the statements. And at some point in time, another thread, the orange thread, comes and starts executing. With wavefront threading in Kanagawa, we can say the blue thread is ahead of the orange thread, and that's the phrase we use in the paper. And that relationship stays constant over time, so the blue thread will stay ahead of the orange one. And there's all these details you can read in the paper about how that ahead of relationship relates to control flow constructs in the language. And that was a bit hand-wavy. You could say, what is it exactly they're executing in order? Is it lines of code? Is it statements? What is it? And the answer is it's access to shared state. So every variable is either thread local or it's shared between threads. And it's the accesses to the variables that are shared between threads. That's what executes in order when you get down to it. So if you really want to be precise, you call this a memory consistency model. And there's two parts to the definition. We call it wavefront consistency. The first looks like what you would see in a definition of sequential consistency. And that is, from the point of view of a given thread, all the accesses occur in program order. The second, here's our secret sauce. If a given thread is ahead of another one, and they're both going to perform the same shared memory access, then the thread that's ahead will perform the memory access first. This is it right here. This, if you want to boil Kanagawa down into one thing, that was it right there. And I'm going to spend a few slides with some animations describing this. So on the left here is just, it's valid Kanagawa code. It's just a boring old sequential loop. And on the right is a graph depicting sort of the dependencies here. So in each column is the statements for a given iteration, and then the rectangles represent each statement, and then we have the edges. So the vertical edges represent the requirement that for a given iteration, the statements run in order. The edges that go between the columns say that a given iteration cannot start until the previous iteration finishes. And this is just the standard semantics for a sequential loop. Many languages have parallel loops, which remove the dependence between the columns, and you can say each iteration is run by a different thread, or another way of saying that is, any thread can start this at any time at once, any thread can finish, they can overtake each other, it's kind of the Wild West. And this, again, on the left is valid Kanagawa code. Now here we go, here's a pipeline loop. We call it pipeline 4. Similar thing, we're saying, here's a loop, here's the loop body, I'm going to spin up 3 threads that'll execute the loop body. But I've got these right arrows in the control graph here. And those are the requirements from Wavefront consistency, our consistency model. So what they're saying is, like the first statement, it must be run by iteration 0 first. So here's an example. So like the blue thread is doing iteration 0. It has to go first. There is no choice. Once it moves down to the next shared memory access, and on this, for just simplicity, I said every line has a shared memory access. That sort of makes room for iteration 1, which is processed by the orange thread. And once it moves down, that makes room for iteration 2, which is processed by the purple thread here. And so what this does, it illustrates is that our memory consistency model gives us this inherently pipeline semantics, where threads flow from the top to the bottom through the imperative code, and they stay in order. So now I'm going to spend a few slides talking about how this maps to hardware. And the point is, it's a very obvious, straightforward, predictable mapping. You're not relying on the compiler to do really anything smart or a global optimization. So here's how just a sequence of straight line code maps to a pipeline. On the left is the code, the right is the pipeline. Here's a thread that enters. That plus might be scheduled on the first pipeline stage. Then it moves down to the next line of code, which has another plus that'll be scheduled on the second pipeline stage. Same colors as before. And so on the left, you see the threads flowing through the statements. On the right, it's data flowing through a pipeline. Pretty straightforward. Now we're going to talk about control flow. So here's a sequential loop. And on the left, I just said body as a placeholder. That means whatever the body is. On the right, here's the hardware. And the purple rounded rectangle is, again, sort of a placeholder. It means whatever hardware would be generated by the body of the loop, whatever it is. A sequential loop is essentially just this backward link. It says when a thread gets to the bottom, it makes a choice. Am I done looping, in which case I keep going down, I leave, or I return for another trip around the loop. Now here's a pipeline loop, again, pipeline 4. That's the same construct we talked about before. So when we start running a pipeline 4 loop, there's a little FSM in the hardware that will dispatch the threads. In this case, it's 2 threads. Then whatever is the body of the loop, and then at the bottom we have a little FSM that collects those 2 threads and sort of waits for them to both get there. Pretty straightforward. Now we're going to talk about composition. So here's, again, the same hardware for a pipeline loop. I'd switch the body to green. And remember, the body green is a placeholder. Here's a sequential loop. Again, same picture I showed you before. And now, very straightforward. Take that thing on the right and substitute it in where the green rectangle is. And that's how you say a sequential loop nested inside a pipeline loop. And the point is, the hardware composes in a way that's very analogous to the control flow. And the programmer just gets this in their mind and says, oh, I understand how the hardware is going to compose just like the control flow is, and therefore I can predict my performance very accurately. And at no point in this process is the compiler doing an optimization like, here's a sequential loop, but I realize I think I can pipeline it and get better performance while maintaining the illusion that it's running sequentially. And sort of, if that optimization works out well, you get great performance. If that optimization fails, you get horrible performance. That's not the model here. The compiler is very straightforward. And if you want good performance, essentially you have a lot of threads. If you have a lot of threads, your hardware is highly utilized. In addition, well, yeah, fine, here's nesting the other way around, where you have a sequential loop that contains a pipeline loop. Similar thing, it's just we've moved that backwards edge to around the outside. And finally, just to like beat this dead horse, here's a loop right after another loop. And so there's a pipeline loop on top and a sequential loop on bottom, and there's the hardware you get. It's all very straightforward. I think from a software point of view, this is like, duh, obviously. But from a hardware point of view, it's kind of a novel thing that you just get this predictable performance and composition from imperative code without the compiler doing really heroic work. So if you combine this predictability and the ability to compose things with predictable performance with well-established techniques from imperative and functional programming, to write composable code, it enables the development of a horizontal library. And an example of this, the pipeline for and the parallel for functions I showed you before, those are actually library functions. When the code is open source, you can go see the library is actually quite large, and it's horizontal, like the STL and C++. It's not like, here's the graphics library and the compression library. It's more like general algorithms and data structures and utilities to let you compose code. I'm going to spend 3 slides talking about the difficulty of reasoning, or the ease of reasoning about this as compared to traditional multithreading from 3 different points of view. The first was inspired by this blog post by Hillel Wayne, who said, don't make fancy arguments about psychology and how hard it is for humans to think about things happening at the same time. Just count the number of possible executions for a piece of code. And if there's many possibilities, it's hard to reason about. And if there's few possibilities, it's easier to reason about. In terms of the graphs I've been showing, what you want to think about is how many ways can I topologically sort these graphs. So on the left here is the graph for a parallel for loop, and on the right is the pipeline for loop. And I think it's pretty obvious on the right, there's many, many fewer ways to topologically sort that graph than on the left. For example, like I said before, when you topologically sort the graph on the right, there's only one option. It's the I0 thing in the top left. That's the only option. Whereas if you're topologically sorting the thing on the left, any of those rectangles at the top are valid. So there's just fewer possibilities, which makes it easier to reason about. Another standard technique for many languages is to reduce the number of possibilities, is to combine multiple statements into a single atomic statement that can't interleave. And we have that as a first-class feature in Kanagawa. We call it a scheduling constraint. And here's an example of one type of scheduling constraint, the atomic block. From the language point of view, this means one thread at a time in the block, and there's no torn reads or writes. From the hardware point of view, it means all that code runs in a single pipeline stage. And we have another more general way to express scheduling constraints. Here's the last sort of putting it all together. I'm going to give you a big example, but it's a simple idea. It's the idea, you can say I have a group of threads, and I can say this one's the first, and this one's the last. And that property stays constant over time. And you can reason about that and use just that as a synchronization construct. And it really simplifies the reasoning about multi-threaded code. So here's another library function we have called pipeline last. Again, it models a pipeline loop, but it can return a value. And the value it returns is the value returned by the thread that handled the last iteration. So just describing sort of the semantics of this pipeline last function, you can only have this if you have the notion of a thread that is the last one, and that property of being the last one stays constant. And you'll see in the body of the loop here, there's this isFirst variable where a thread can determine very easily, am I the first thread in a group? And then that property stays constant over time. And in the atomic block at the bottom, it uses that property to say, if I'm the first thread, I will sort of clear this shared accumulator variable called sum. Whatever was there before, I'll just ignore it and clear it. And all the other threads, they just add to it. And so it's this very simple concept of saying threads have an order, they stay in order. And I can use that itself as a synchronization mechanism. All right. I'm going to talk about, there's a lot of results in the paper, a lot of them comparing Kanagawa code against handwritten RTL. Though I'm going to talk about the one I'm most proud of here, and this is a pipeline processor. So here's a quote from a paper in 2019 that says, if you write an instruction set simulator or an interpreter and give that to an HLS tool, you're not going to get good performance. And I think this is very true for industrial HLS tools. And the point is it's a pretty tricky problem. You have to sort of speculate about branches, and your source code is sequential. And so you're putting a lot of responsibility on the compiler. And one tact you could take with this is saying, well, the compiler's not smart enough. Let's stick with a sequential language and make the compiler even smarter. But the tact we take is say, let's write a multi-threaded instruction set simulator with this wavefront threading. And it's not one thread per pipeline stage. It's one thread per instruction. And the threads flow through the pipeline. And if you do that, the code is really elegant. It's concise. It's abstract. And it's very parameterizable. And if you compile it as a soft processor on an Altera FPGA, you get good perf. So we have a RISC-V processor. Against the Neos 5 from Altera, perf per area, it does very well. You could say the Neos 5 is kind of new and not mature, and it will get better. If you want, you can also compare against the Neos 2F, which is a much more mature implementation from Altera, but different instruction set. So it's a bit apples to oranges. If you do that comparison, they're head-to-head. But the Kanagawa one, the source code is just beautiful, in my opinion. So I'm just going to make sure I hit all the points. Yeah, so this is kind of a real thing. We've transitioned from science project to real thing. Engineers at Microsoft are willing to take a bet on it for FPGA accelerators, and it is IP generated by our tool is broadly deployed on FPGAs. We've got this very broad horizontal library made possible by the fact that you can fearlessly compose code, and like you can compose code written by different people or at different points in time. And we plan to open source it. I'm going to summarize here with just some open problems that we would be interested in collaboration on. The first is, can you compile this Wavefront threaded code to other architectures? It is easier to reason about than traditional multi-threading. And you could imagine saying, okay, one of these Kanagawa threads, I'll fill my SIMD lanes with it, just like a GPU fills its SIMD lanes with threads. Or you could say, I'm going to utilize my cores in a many-core processor, or I'm going to use my nodes in an HPC cluster. I think if this worked out, open question, it would be really powerful because, again, the source code is much easier to think about, and you just have much less chance for race conditions than traditional multi-threaded code. Another aspect here is machine understanding. Compared to hardware, there's a lot of details missing. And so I would think machines could do a better job understanding and generating the code. And again, compared to traditional multi-threaded code, it should be easier because there's fewer possibilities. So we had one successful intern blaze a path here and find some promising directions on the formal verification point of view, like how you do formal verification of Kanagawa code at the source level. And then it seems really interesting to look at large language models generating Kanagawa code. There's additions to the language. Our general philosophy is don't make the compiler smart. Extend the language. If we find some problem, like some circuit you can't express or some inefficiency, we find a way to extend the language to solve that problem rather than add heroics to the compiler. So I've got some examples of here. Some of the things I heard yesterday were inspiring, like the Descend talk. I think that something like that might be relevant. And finally, there's improvements to the tool chain. So I wrote up here the automated ECO support. There's a lot of them. If you don't know what an ECO is, you can come ask me afterwards, and I'll explain the gory details. It's a bit scary. That's it. Thank you.
Great. Thanks, Blake. Questions?
Thank you for extremely exciting work. And I have several questions, but I would say most of them for offline discussions. My primary question is that how do you deal with dependencies among multiple threads or headers between multiple threads?
Headers? Is that what you said?
Yeah.
Oh, hazards.
Yeah.
Yeah, the processor is the perfect example. That's why I chose to show it.
Yeah.
Because you can't do a good processor unless you can handle control dependencies and data dependencies.
Yeah.
Or hazards, I mean. Yeah, and the way they're modeled is shared state. So you have some variables that are local to each thread, and each thread logically has its own copy. You have some variables that are shared between threads. The way all the hazards are handled with these shared variables. And when you write to them and you read from them at the correct point, and you use the scheduling constraints like I showed. Yep. That's the way to do it. And in the library, we have all sorts of synchronization objects, like what you would see in software, like mutex and semaphore, built on top of those.
I see. Thank you.
Hi, you presented that there are two ways, there are multiple ways to have your your for loops, and you presented sort of like the pipeline for and the parallel for. And I was wondering, since this is sort of mainly for HLS, what was the benefit of also keeping that parallel for?
Oh, so pipeline 4 has a perf ceiling.
Okay.
The perf ceiling is 1 thread per clock cycle.
Right.
Which can be a lot of perf, because if you have a deep pipeline, 1 thread per clock cycle, that's a lot of work per clock cycle. But if you need to exceed that ceiling, then you use the parallel version. And in the parallel version, you don't get this ordering. Things are unordered between them. So a typical use case is, I'll generate one pipeline. It might be 500 lines of Kanagawa code all up. And that's pretty good. And I get most of my parallelism there, just in the pipeline parallelism. But then I might do 2x or 4x replicas of that, because I need 2x or 4x more perf, and I'll do the parallel version there.
Right, okay. And in that case, you would use sort of like the semaphores and locks you have access to in the library?
Yes.
Or, yeah, okay. Thanks.
Hi, Jane Chen from University of Cambridge. Thanks for the excellent talk. I got 9 questions, but I'm going to ask the first 2. So you mentioned about the fixed order of the memory access for each thread based on their starting order. That's quite interesting. In other cases, like in softwares, like P threads, like the user wanted to make memory access out of order and then synchronize them using locks. Is that supported in this Kanagawa?
That's the parallel version. So if you use the parallel loop, then you have no ordering that you can rely on, and you have to use locks.
I see.
But typically, you get you write most of your code with the ordered version, and it's just much, much easier to think about.
I see. Yeah, thanks. And the other question is, I find this language very interesting. I want to try play with it. So if I write a simple program in your language and it generates system Verilog, how do I test my system Verilog?
We have an interpreter. That's,
Okay.
that's the simple way, and you don't have to go to Verilog for that.
Is there any way I can generate a test bench as well, like to test the hardware design?
Can you generate a test bench?
Yeah.
So, I mean, a typical thing, you write, for small stuff, you write the test in Kanagawa itself, like in a separate file. And then you can either run that in the interpreter or generate Verilog from that.
I see.
That's very common. We have actually a unit test framework in our libraries.
I see. Got it. Thanks.
Yeah, thank you for the talk. My question was about the different for loop combinators you have. So are those primitives or are they just defined in Kanagawa and you could find different
The
ones?
sequential for loop is part of the language. The pipeline for, pipeline last, parallel for that I showed you are actually library functions. If you look at them, they actually take lambdas as the body. You see, this looks like a C++ lambda as the body.
Yeah.
So that's actually the library function built on lower level
So
things.
the pipeline last is not a primitive, it's
Yeah,
an actual
right.
Kanagawa function.
Yes, and one thing that we do, and we're going to keep doing, is make the language more general, more low level, and move things from the language to the libraries.
Thank you.
All right. Well, thank you, Blake. Great way to close out a very fun session. Thanks for that talk.
Thank you.